Today's problem is maximum non-adjacent nodes sum given the root difficulty medium. Given the root of a binary tree with integer values, your task is to select a subset of nodes such that the sum of their values is maximized with the condition that no two selected nodes are directly connected. That is, if a node is included in the subset, neither its parent nor its children can be included. Okay, example. Well, this one's pretty simple. I mean, the best choice is to just take the 11. This one threw me off a little bit. So we have, well, the best we can do is to sum the 4, 5, 6. How much is that? 4, 9, 6, 15. And then we can also use the 1, so that's 16. So what it looks like here is it would be a good idea to just do a breadth first search, like a level order traversal, and we can sum up all the odd levels and we can sum up all the even levels and just take whichever one is bigger. Then I saw another example like this. Now this tree here, the best we can do is 17, but that is not a level order traversal. So, I have to throw out the level order traversal idea. So we know that a node and its immediate children can't be in the sum at the same time. So we could do a recursive approach where we do a couple of things. One is include the current node's value in the sum. In that case, we can't include the values of the immediate children, so we can recursively call the function to include the values. We can recursively call the function on the grandchildren of the current node and include their values. Then we do a second thing, which is we can exclude the current node's value in the sum. And in that case, we're allowed to include the values of the immediate children. So recursively call the function on the immediate children, include their values, choose the max from both sides. Now, if we did that, we're going to have overlapping subproblems. For example, if we start at the root node, we include the 1. Now we can call the recursive function on the grandchildren of 1, including, say, 5 and 6. If we exclude the 1, then we go down to node 3. We can call the function on the children of 1. If we exclude 1, but if we include 3, then we have to handle the possibility of also excluding 3, and so that's going to also call the method on 5 and 6. So okay, it's overlapping subproblem. The point is, if you did it recursively, you would want to do it. You would want to re-implement it as top-down dynamic programming. Now, there's nothing in here or anything that suggests that they want to see a dynamic programming solution. So, okay, so the approach that we're going to use is one in which we are going to return a list for each node in the tree. There's going to be a pair of values in there. The first pair indicates the maximum sum when the data of the node is included, and the second value indicates the maximum sum when the data is excluded, and that is included here as a comment. All right. So let's see how this would work. Okay, I want to try to do this here. I need to scoot that over a little bit. Okay, and that means I'm going to have to scoot this over a little bit. Is everything still visible? Whoops. Let's bring that other one back. Okay, yeah, I think so. Okay. So the first call is to max sum helper with the root, and the root here is 1. So 1 comes in, and then the first thing that we have to do, because the root is not null, first thing we have to do is get the max value from the left subtree, and then the max value from the right subtree. Well, I sort of misstated that. I mean, we're going to get 2 values here from the left subtree. We're going to call max sum helper with root left. That's the 2. And that's going to return a list of 2 values. The best value we can get including the 2, and the best value we can get excluding the 2. Well, it turns out that the best value we can get including the 2 is 2. Because if we use the 2, we can't use the 12. The best value we can get excluding the 2 is 12. So what we're going to get back from this is 2 and 12. Okay, then we call max sum helper with root right. That would be the 15. Okay, what is the best? Well, now again, that's going to return a list of 2 values. The best sum we can get from that right subtree if we include the 15 is 15. Now the best value we can get from that right subtree if we exclude the 15 is 7. So that is going to return, again, 2 values, 15 and 7. Now we'll figure out, oh, I can't do that. Okay. We're going to figure out what is better here. We're back at the root now. We have the left subtree, we have the right subtree results. What if we include the root data, which is a 1? And then we would have to include the value of the left subtree and right subtree with the 2 and 15 excluded. Okay? The best we can get from the left is 12. The best we can get from the right is 7. So the total there, if we include the root, the 1, is 1 plus 12, 13 plus 3 is 16 plus 4 is 20. What about exclude? All right, exclude, we get the max of the 2 values from the left subtree. That would be whether or not we include the 2. So those values would be including the 2, 2. Excluding the 2, 12. So we'll take the 12. We'll also take the max we can get from the right subtree, including the 15 and not including the 15. Okay, so we want to include the 15. The best we can get from the right is 15. So 12, 15, 27, that's the best we can do. So that is our method. Let me get rid of this and see if we can run this. Move that over a little bit, and go. Okay. Let's see, is there anything else to say about this? I don't think so. Again, there is a recursive solution. I mean, that it's probably the most straightforward solution. But again, if you did that, you're going to have repeating, or you're going to have overlapping subproblems. So you would want to convert it to a top-down dynamic programming, and since that doesn't seem to be what they want here, we go with another approach, which actually I think it's a pretty clean approach. So okay. You can like the video. I hope you do. Subscribe to the channel, and we will see you next time.